My name is Nathan Glover, and today I'm going to take you through part 2 of my hand map project. Today I'm going to be focusing on the project update and reviewing some of the previous decisions I've made and rescoping. So I'll briefly take you through what we got through last time. I spoke about the resources and tools I would be using, edge detection's use case and some of the issues I was likely to face, the HAR classification, along with some of the fundamental problems associated with having an incomplete image set, and I spoke of a hybrid solution that I was looking to implement. It became clear once I'd attended a meeting with some of the people from Princess Margaret Hospital, and after I'd spoken to my unit coordinator, that I would need to rescope the direction of my project. Generating splints is something that would be a goal later on, however it's not my priority at this point in time. The current goal is to map the characteristics of a hand, the convex and concave points, with reference to a static point on the hand, while also providing angular vectors indicating how far parts of the hand are bending from a static reference point, or angular mapping. The image on the right gives you an example of this. The hand has convex and concave points, which are elements of the outline of the hand that change direction very quickly. We also have a static point in the center of the hand. This static point would be the same on every hand, or at least that would be the aim. We could then get a distance vector from each of the concave and convex points to that static point. I'll now give you a brief overview of the angle mapping. The aforementioned distance vectors will primarily be used to map angles in the bend of the hand. I'm using the department supplied coloured sensor cube as a reference point. The cube has sensors that provide my system with positional and gravitational data. This data will give me a very important earthly constant of gravity, or 9.8 meters per second squared. We love you, gravity. Don't ever change. Seriously, don't. The process that I hope to follow in order to map the angles successfully will begin with me sensing whether or not the cube is in the image. If there is, I will extract gravitational data from it over a standard communications protocol, more likely Bluetooth or wireless. I will then draw a vertical line below the box and another line showing the offset from the line in reference to the cube sensor. This line symbolizes the true downward force, and the other line will symbolize the offset of gravity, i.e. the angle offset. The next part is to use the peak point of the wrist and draw a line straight up. I will use this temporary line in reference to another temporary line from the center of the cube to work out the angular difference of the bend in reference to the cube. The final step in angle mapping is box transformation. This is a step that I'm not sure I'll need yet, but if I do, I will take the height of the box and construct an imaginary replica of the current box at another position down the arm. I'll be able to use that reference point for my other angle. This angle would be the last piece of information I'd need to get a fairly accurate plot of the bending angles on either side of the wrist. I'd like to briefly address some of the problems I know I'm going to have to deal with throughout the angle mapping problem. The first being an unknown scale, which leads to the issue where I can't compute angles because I don't have any accurate way of calculating distance. My solution is to simply have a line or a marker printed on the side of the box with a measurement or a length of exactly 1 centimeter. This line can be used as a size or scaling reference point to be used in the final calculation. My second issue is more of an observation than an issue, but this method only works side on. The final implementation will more than likely require a top-down view anyway, so I don't think this is a problem. The third problem I'd like to address is with the high wrist point. What if the highest point of the hand isn't the bend in the wrist? Well, I don't think I can use the highest point anyway, so I'm going to be using contour mapping and feature detection methods to identify the pisiform bone. That will be considered the primary axis. The pisiform bone is used as it's predominantly visible on most people's wrists. It's that little bump. Next, let's discuss hand and box detection methods and how I plan to do that. And it's a wonderful question because there's a lot of possible answers. I've been working on two promising methods, RGB and HSV method, which is color detection applied to a small colored box. That's again supplied by the department. And second is contour mapping and the application of a convex hull, which I'll go over in a second. I'd like to discuss first why I've chosen color as my primary method of detecting objects. Well, the computational resources required to process the RGB and HSV values in an image are considerably lower compared to that of other algorithms. This makes it a perfect starting method for quickly singling out the cube on the hand and lower the search area for my other more computationally expensive algorithms to go over. Cube colors are also very distinct, so there will be a high chance that the largest object that I'm looking to detect in a scene will also be the cube that I'm searching for. During my initial testing, I used a tutorial by Adrian Rosebrock to quickly set up a rudimentary color detection system. The code tutorial supplied was originally used to detect the Pokemon Blue game cartridge with a similar output to the image below. The code on the right is a brief overview of what you'll need to set that up. And now for the results. The test for this system worked considerably well for the first attempt on the blue block, because blue is a very interesting color, because it isn't really commonly seen in this particular shade that I was targeting. Yellow, on the other hand, turned out to be a very, very prominent color in practically everything, like the walls, everything around me. The results in the yellow tests were actually pretty terrifying. It was also very difficult to manually find and calibrate the RGB colors, because I'd constantly have to recompile and rerun code to view outputs. So I took it upon myself to build a simple GUI application that could deal with this for me, called Bounded RGB. I've put the project up on my GitHub, or under the project's GitHub, if anyone would like to follow or add to it. Hopefully I'll be able to use this little application when calibrating my system for new objects with different colors. It wasn't too long until I had a small system set up that could handle real-time tracking of colored objects. You can see on the right that the camera tracks and provides a little tail of where the box was detected and where the box is moving to. The tracking is solely based on RGB values, and the Python code for this example can be found on the project blog. Next, I decided I'd start working on a convex hull and contour mapping techniques for my image processing. I've mentioned bounding boxes before, and that's kind of what I meant by convex hull. It's just a line that runs around the outside of the convex points of my image. I worked on the contour mapping and convex hull in C++. My reason for this is I wanted to expose myself to the native language that OpenCV was written for. It added some complexities at first, especially with the project setup, and I've actually provided the cmakelist.txt file that I used to compile the project with cline on the right-hand side in the slide. Hopefully I'll see better performances at runtime when I'm working with more complex image transformations. The contour mapping process can be seen in this slide. 1. I position the hand in an area with little background interference. I manually calibrate the HSV values until the hand is visibly the largest detected object in the image. 3rd, I draw a green line around the largest contour found in the image. And 4, I calculate and map concave and convex defects. These points, or defects, are planes that quickly change direction, as I explained before. Finally, a convex hull is drawn around the outside of the entire object. These boundaries will later be used for distance mapping, and can be seen in the image or the GIF up above. Note that this method is still very sensitive to changes in environmental lighting. You can see in the image below that a slight change in light will completely throw off the calibrations. Before concluding, I'd like to quickly discuss one of the interesting issues and solutions I came up with while dealing with OpenCV on Mac OS Sierra. It's really painful. Installing through Homebrew results in numerous errors, which I've documented in my project blog. Once I'd finally fixed it, it came with the added benefit of not having to work out of a virtual machine, while it's also giving me access to OpenCV with the C++ bindings and Java environment. My plans coming up would be to take the edges generated between the various points in the image and measure the distances. I want to also implement a way to detect the line on the box and use it to scale my distance calculations. Then, implement angle calculation methods discussed at the start of this presentation. And finally, I'd like to also test performance between C++ and Python and see if there's any need for me to port my existing Python code over to a faster language. I'd also like to mention that I haven't completely ruled out the use of a hard classifier, and sometime in the future I might be able to get access to some images that I'm able to use to produce a very, very powerful classification engine that I could use in conjunction with my color mapping. Hopefully this comes through. Thank you for viewing my presentation, and I hope it's been informative. If you have any information that you'd like to provide to me, please feel free to flick me an email at nathan@glovers.id.au or check out my project blog at handmap.github.io.